Hello, welcome back to another episode of Math with Haas. So, you are watching Precalculus Season 1, Episode 8. We are continuing our discussion of logarithms and exponential functions. So, right now we have four properties of logs, and we have one law of log. So here's our properties. We have log base b of b to the x is equal to x, b to the log base b of x is equal to x, and we have log base b of 1 is equal to 0, log base b of b is equal to 1, and we had these laws also where log base b of a to c is equal to c log base b of a. Now there are two more laws of logs that we must consider, and let's go ahead and dive right on in. So the first law of logs that we are going to talk about is the following. So we have log base b of a times, let's use a c, I guess. So inside the log here is two quantities being multiplied by each other, and it turns out that we can break this up into a sum of two logs, so log base b of a plus log base b of c. Now we must keep in mind that this is not the same thing, so it's not the same thing as log of a plus c. Alright, so log of a plus c is not the same thing as log of a plus log of c, and it's not the same thing as log of a times c. So keep this in mind. We don't have a rule for this quantity here. So if there's an a plus c inside a log, you just leave it as a plus c unless you can simplify the addition. So that right there is a pitfall many students usually have. Let's go ahead and prove our new law logs here, this fun fact. So let's let a equal log base b of a, and let c equal log base b of c. So we can rewrite each of these as exponentials now. So we have a is equal, we have b to the a is equal to a, and b to the c is equal to c. Alright. Now, if we think of the quantity a times c, that's the same thing as b to the a times b to the c, which is the same thing as b to the a plus c, using our exponent rule, where if you have x to the y times x to the z, that's the same thing as x to the y plus z. Now, let's see, we can take the log of both sides now. So if we take the log of the left and the right, we would have log base b of ac is equal to log base b of b to the a plus c power. Now notice our exponential base is the same as our log base, and we can effectively nuke all that. So let's put a big fat X there. Since the bases are the same, those cancel out, so you get log base b of ac is equal to a plus c. Well, if we look up here, a is equal to this log, c is equal to this log, so log base b of ac is equal to log base b of a plus log base b of c. And that is what we need to demonstrate, so proof done. Alright, so that is our second law of logs. There is one more, and it will look very similar. So our last law of logs is the following. Log base b of a over c is equal to log base b of a minus log base b of c. That's a small c, we'll make it bigger. So when there's addition, or I mean when there's multiplication inside of log, then we had addition out here. Now when we have division, we get subtraction. The proof for the addition is very similar to that of the proof of the law of logs with the multiplication side to log is very similar to that with the division. And we can go ahead and do that real quick. So we have, let's see here, let's just say a is equal to log base b of a, and c is equal to log base b of c. Then we can rewrite each of these as exponentials. So we got b to the a is equal to a, b to the c is equal to big C. And then we can divide these. A over c is equal to b to the a over b to the c. And then we can use our exponent laws here on the right side. So that's the same thing as b to the a minus c power. So we have a over c is equal to b to the a minus c. And now we can take the log of both sides. So log base b of a over c is equal to log base b of b to the a minus c. Keep in mind what you do to the left side is equal to the right side. So we log one side, you have to log the other side. Now on the right side again, notice the bases are the same, so we'll kill those off. That leaves us with log base b of a over c is equal to a minus c, and a and c are both our logarithms right here. So all we need to do now is substitute those back in, and we have proved our law of logs. So log base b of a over c is equal to log base b of a minus log base b of c. End of proof. Alright, so let's go ahead and scroll up and we'll add our last two fun facts to our list here. Log base b of ab is equal to log base b of a, let's see, plus log base b of c, log base b of, oh, why did I put a b there? So that needs to be a c. Log base b of a over c is equal to log base b of a minus log base b of c. So that is, let's zoom out a little bit. There is all of our fun facts about logarithms right there. Besides the domain and range properties, of course. Alright. So, with this comes new examples. So, what we want to do is practice combining and expanding log expressions. So, expanding. So, if we have, for example, log of xy, well, we'll call this example. We can expand this using our addition rule for laws of logs. So log of x plus log of y, or I should say our multiplication law. Second example, if we have, say, log of x, y, z, well, we can think of it as this quantity in blue times this quantity in green. So we get log of xy plus log of z. Then we can apply our multiplication rule again and have log of x plus log y plus log z. So here we used the multiplication rule 2 times. We use it first to recognize that you have a quantity here in blue, the xy times the z, and then we used it again to break up this xy. Another example will be something, let's make it spicy. Log of x cubed y to the 1/4 over z. So here's a more interesting problem. So the way you want to think about this one is you have a quantity divided by a quantity. So here I notice we have a fraction. So I'm going to consider everything in the green box as numerator. That's like so if we use our law logs for division, we have log of x cubed y to the 1/4 minus our denominator, log of z. Now we have multiplication here. We got a x cubed and a y to the 1/4. So we can break this up as log of x cubed plus log of y to the 1/4 minus log of z. Now our last step is noting that we have these exponents here, so we can use our other law log with for exponents. So that means these exponents, they will come out in front as coefficients. So we get 3 log x plus 1/4 log y minus log z. That's our final answer. We'll box that one, because we actually did some work. Now, I might try and trip you up with this one. Log of, how about 5th root of x squared over y cubed. That's a weird one. I should have made it more obvious that that is nothing to do with that. I should have that down more. Anyways, we have the 5th root of x. What we need to realize is whenever you have this situation here, the nth root of x, that's the same thing as x to the 1 over n power. So we are going to first rewrite this as exponents. So we have log of x cubed over y cubed, x squared over y cubed. This is to the 1/5 power, and all of this is inside our log. Now you have two options. You can move this 1/5 exponent out front, or you can, well, that would be using the law of logs, or you can distribute using your exponent rules. So it doesn't really matter which way we go. I think what I'll do is just distribute here. So we got log of x to the 2/5 over y to the 3/5. Now we can recognize that we have a quantity divided by a quantity, and so we can use our division. So we have log of x to the 2/5 minus log of y to the 3/5. And this is, now we need to use our exponent rule. 2/5 log x minus 3/5 log y. Alright, let's pause there for a moment and take a look at what we are doing here. So for our last two examples, 3 and 4, what we were doing is essentially peeling back the layers. So we can imagine we have this division here as like the outermost thing going on. This division affects everything going on, so we wanted to deal with that first. Once we dealt with that, we noticed that right here we had this multiplication that we next needed to deal with. Once we did the multiplication, then we had to take care of the exponents. In this case here, we had the root we had to first deal with. we need to take care of this because it was the outermost thing affecting everything inside the log. Once we took care of that, then the division was the next step. We want to think of it as peeling back the layers. This is kind of the outermost layer. This would be the next layer. Once we peeled back the division, we had the exponents we had to peel off, and then that left us was just a log of a variable. So that's how you want to think about this. As you expand it, we're just kind of peeling back the layers. Alright. Now, for these next set of examples, we want to think of combining. Okay. So examples combining. So our first example, let's say log of x minus log y minus 3 log z. So this one's a little weird because there's a double negative. How you want to think about it is, well, we can think of it this way. I'm going to do that. So how I like to think about it is by focusing on this quantity right here. Yeah. So if we focus on this quantity, this is just going to be off on the side. So if we think about this, this is just simply applying our logs for division. So log of x over y. Now notice we did not do anything about this quantity here, so this just hangs out. Our next step, we need to take into consideration now just log of z. Now before we do anything, if we look at our laws of logs up here, where are they at? So if we look at our laws of logs here, notice for multiplication or division, there are no coefficients in front. So in order to use these, we must get rid of the coefficients. So when we scroll down here, let's take a look. We have coefficients. We got this coefficient right here that we just highlighted. This coefficient we must move inside using the law of logs. So that's what we'll do. So we have log of x over y is equal to, not equal, and then minus log of z cubed. Now there's really two options we could have done. We could have moved a negative 3 inside, so I have z to negative 3 and then have a plus sign here, or you can just move the 3 in and keep the negative there. It doesn't matter which way you go, you will get the same answer. Now at this step, we can just note that, well, this is the same as before, you just have a log minus a log now. So I can now use the division rule again. So we have log of x over y divided by z cubed. Now if you give me as this if you give this to me as your answer, I will mark you down wrong because you need to simplify that. Simple as that. So to simplify it, we have our x divided by y divided by z cubed. I claim that this z cubed will go in the denominator with the y. So if you're wondering why, you could think of it this way with the invert multiply with the fractions. Think of fractions by fractions. So you have x over y times 1 over z cubed. So you can work it out that way. The way I like to think about it is if you have a fraction divided by another quantity, that other quantity will always just go in the denominator. So it didn't matter what the z cubed was, it always show up in a denominator. Unless of course it's a fraction or have a negative exponent, because that will change things. So this is our answer here, combining. Another example. How about 1/5 log x plus 1/4 log y minus pi log z. Alright. So in this case, it doesn't really matter the order we do. Doesn't matter if you take care of the addition first or the subtraction first. What does matter, however, is these coefficients. This must be done first before we tackle the addition or subtraction. So, using our law logs, we have the following. Alright. So that looks nice. I think I'll take care of the plus. So this will become multiplication. So you have log of x to the 1/5, y to the 1/4, and quantity minus log of z to the pi, which with that negative we can use our division rule again. So that gives us log of x to 1/5, y to 1/4 over z to the pi. Alright. And with that, we are going to conclude this video. Thank you for watching another episode of Math with Haas. We appreciate your audience and viewership. If you've been enjoying our content, please subscribe, support us on Patreon, and see you next time. Thank you for joining the Math Party.